Welcome to the AI for You Cafe. Today we have a special cafe on the LEGaTO project with 4 speakers, which is really special. And I'm very happy. And I'm sorry, now even I get a call. No. Sorry for the interruption. You see, the cafe is now perfect. And so, one moment. I welcome today is Osman Unzal from Barcelona Supercomputer Center. Hi, Osman.
Hi.
Hello. Hi. And our special guest, last moment special guest coming, Pira Noor Somro from Chalmers University. Great you're here. And Nils Kuksar from Bielefeld University. Hello. And hopefully soon Hans Salomonsen, and he will come later into our cafe. The title of today is Energy Efficient AI, a Perspective from the LEGaTO project. My name is Carmen McWilliams, and I'm the moderator and organizer of the cafe, and I'm partner in the European AI project. So just again to repeat fast the little rules here, the session will be recorded. No confidential information shall be shared in this cafe session. In this cafe, the speakers express their personal view and opinions. That is not necessarily the official AI project opinion. So what are we doing here? This is an online cafe, and we share insights into the European AI scene. Participants get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research and application. And it's interactive. You have the chance as participants to write your questions. On the right side in the control panel, there's a chat question menu, and you can write them in, and after the presentations I will read them to the speakers. So great, you're all there, all the participants out there, and thank you that all the speakers are here, and we start with our program. The first speaker will be Osman Unzal, and I shortly introduce Osman, and also I will introduce Pira because they're together making the first presentation. Osman co-leads the Computer Architecture for Parallel Paradigms research group at Barcelona Supercomputing Center. His main research interests are in computer architecture, fault tolerance, energy efficiency, and transactional memory. He will introduce the LEGaTO project and give an overview of the energy saving theme of the project. And with him is Pira Noor Somro from Chalmers University. So now I give the moderator role to Osman and afterwards to Pira, and welcome once more in this cafe. So Osman has now the moderator role. He can now take over.
Thank you very much, Carmen. Can you see my screen?
Everything is perfect.
Okay, thank you very much. As Carmen mentioned, I want to have this change my screen. Just a second. Yes. We are going to look at the use of AI in the LEGaTO low energy heterogeneous computing project. I'm the coordinator. My name is Osman Ünsal. And the reason for the project, which is an H2020 project, is that the challenge that we have in computing is not floating point operations per second, but in megawatts now. So we started from this point. The main focus of the project is energy efficiency with the data center and edge focus specifically. Okay. And how did we get here? Moore's law, as we know, is slowing down. So that we cannot fit 2x number of transistors anymore across generations. So this necessitated a move towards accelerators, special purpose functional units that we can fit in the available area. Gives a better utilization, let's say, for the limited transistor budget that we have, more energy efficient, and therefore move into heterogeneous computing. To explore new architectures and models of computation is what it brings together with this heterogeneity. So the model of computation is key. Accelerators are important. GPUs have been used, especially, I would say, for the neural network, let's say, segment of the AI area. They are doing a very good job training and inference. On the inference, they have this 16 bits floating point units. FPGAs are also interesting. So they have been like a latecomer to the show, let's say, of these accelerators for neural networks for AI. But their advantage compared to GPU is their reconfigurability on one side, and they can also shrink the number of bits that they can operate with. That's really good for the inference side. So, and we can build ultra deep, highly efficient pipelines using FPGAs. The ambition of LEGaTO is to create software stack support for energy efficient heterogeneous computing. We start by our partner developed efficient heterogeneous hardware substrate with CPU, GPU, and FPGA, as well as FPGA-based data flow engines, all together in the same chassis. And we put on top of that, and we develop a made in Europe mature software stack for energy efficiency. So together with this goal of energy efficiency, we strive for one order of magnitude in energy efficiency. We also have let's say, side goals of keeping energy efficiency in mind, to be fault tolerant, to be productive here, and as well as to be secure. So those are also goals of the project as well. When we look at it, at the center is we have our software energy efficient tool set, together with fault tolerance, security, and productivity goals, in addition to energy efficiency, running on heterogeneous hardware platforms, and with some use cases that I'm going to come shortly. So we have 10 partners. I'm from Barcelona Supercomputing Center. In today's talk, we will have partners representing Chalmers, Bielefeld, and Embeddle in the other talks. So you can have an idea of the various kind of things that we are doing in the project. We cover 4 use cases, some of which are really relevant for AI. The first one is healthcare. When we started the project 3 years ago, we took the specific subtopic of healthcare, infection biomarkers, a lot of statistical processing, very heavy computational workloads being used, and the idea is to indicate the presence, absence, or severity of a specific disease. So no need to say that this has become even more relevant and urgent in the times that we are living right now. The second use case is the smart home, specifically an assisted living use case, so that we can, there the objective and the relationship to AI is to learn from the user's behavior and anticipate future behavior. So this is also one of the use cases that we have in the project. We have a smart city use case. We have like a weather report, except for pollutant data. It's like a weather prediction city by city. We have a 3D map of Barcelona, and we do this work in the supercomputer that we have in Barcelona. We have a machine learning use case, automated driving and graphics rendering, very direct related use case, and more on that will come a little bit later. And we have a secure IoT gateway, putting energy efficiency and security together. So when we look at the AI techniques or the AI use cases that we have in the project, I would like to start with the healthcare use case. So for the biomarker research, we are leveraging tree-based methods and lasso regression. We have integrated these integration into the SCON security technology that we have in the project, which helps efficient deployment of Intel SGX hardware security extensions. And we have also scheduling techniques to help accelerate one of the key algorithms in the biomarker research using random forest. I will not dwell or detail very much in this aspect in this talk, but if you're interested, I can put you in contact with our partners, Helmholtz Center for Infection Disease Research. They are the ones that are doing this work. In the second use case, we have the smart home use case that I just mentioned. We will talk about the use of AI there. So it will be later presentation by my colleague Niels from Bielefeld. And the last talk today will be the machine learning use case with the details of what we have done in the project, as well as what Embeddle is doing in general. Hans Salomonson will talk about this. And last but not least, immediately following my talk, Pira from Chalmers will give a student research perspective, a quick one on AI, on the topic of scheduling the VGG application across heterogeneous cores in mobile edge devices, specifically the NVIDIA Jetson, which is composed of a heterogeneous core of 4 cores of ARM and the two core of specifically NVIDIA developed Denver 2. So this will immediately follow my talk. And I would like to give a brief overview, very quick, of the undervolting technology that we have developed for neural network. This has been just selected as in a Tetramax technology transfer grant from university, in this case us, to industry, and in this case Embeddle. And so I will talk about the details of this technology. The work has been done as part of the PhD thesis of my colleague Behzad at BSc. The motivation is that power consumption of neural networks is a major issue. We have GPUs, FPGAs, and ASICs that are used for acceleration of neural networks. However, FPGAs are still 10x less power efficient than ASICs. So ASICs such as, for example, the Google TPU, the Havana chips from Intel, the Graph Core Colossus IPU, and I think Sambanova's reconfigurable data flow unit. They're all existing ASICs, all products, and they are. We want to be with FPGAs as flexible, more flexible than the ASICs, which are not flexible. We want to be more flexible, but with a similar power efficiency. How do we do it? We go below the safe voltage. We turn down the voltage below the safe voltage level, and we can get a very significant performance power efficiency gain doing so. We did this study on 5 image classification workloads with 3 different FPGA boards from Xilinx. And if I briefly revisit that we are the neural networks, their advantage is their inherent resilience to errors. So they can withstand a certain number of bit flips here and there. Advantage of FPGAs, higher throughput than GPUs and better flexibility than ASICs. Undervolting reduces power, but then could have some reliability issues because then with the lower voltage, things might not finish in time, and we might get some bit flips. So our goal is to bridge the power efficiency gap, and while at the same time we study the behavior of FPGAs in this undervolting, going below the safe voltage situation for neural networks, and we want to study the effect of environmental temperature. So we looked at 5 CNN image classification workloads seen here. We use Xilinx Vitis platform to map CNN into FPGAs. We use 3 Xilinx different boards. And then we, by using the voltage rails on the FPGAs, we turn the voltage below the safe limit to where below the safe nominal voltage of 850 to around 550. There is a very large guard band where we don't see any errors at all. So this is a very good region that usually the nominal voltage is set much higher than necessary, and we can save very significantly by going below that. Then we get into a critical region, a narrow region where we see errors, and then at the point where we cannot operate anymore. When we look at the results, we see that there's a huge band here where we significantly increase the energy efficiency by more than 2.5x without any faults. And then we start to get into a region where the neural network accuracy starts getting a hit because of these errors starting to happen. Here you can see for the 5 different benchmarks that this is the actually the inference accuracy, and we can see that it takes a hit. However, before it takes a hit, as you can see, there's a huge band that we can exploit. We can have a very large energy efficiency without any detriment to the neural network inference accuracy rate. Then one interesting thing is that when we look at the temperature, somewhat surprisingly, with higher temperatures, you see very interesting behavior here. This is the accuracy. At 50 degrees, you have very high accuracy compared to, let's say, a relatively low temperature of 34. The warmer you keep your FPGA boards, the happier they are with the inference accuracy when you are undervolting. So this was an interesting, let's say, finding that we think could be applied maybe in the future in the data centers. Maybe you don't need to be so aggressive with the cooling out there. So I think this is it from me. I'm a little bit behind. With that, I would like to leave the floor to Pira, who will do a short example of very fresh results that she's getting. Thank you very much.
You're completely on time. Very interesting. I keep now introducing the next speaker, and the next will be Pira. So I give you now the moderator role. As I said before, Pira Noor Somo is from Chalmers University. Pira, do you have it? I put you also on camera. It's me who put you out, so don't worry. I will now make you also seeable. It's not you, it's me. And Pira is coming. Yes, perfect.
Yes, I think my screen is also visible now.
Yes, everything is perfect.
Yeah, okay, thank you. Thank you, Carmen. So, hi everyone. I'm here to talk about my work on scheduling VGG across heterogeneous cores on mobile edge devices. So basically, VGG is a convolutional neural network. And the nature of this use case is to process stream of data, input data, or more specifically, video frames. So I'm basically working on the scheduling of VGG in a pipeline parallel fashion on heterogeneous cores. My framework has actually two modules, uh, an offline module and an online module. So basically, in offline module, I first extract the description of the neural network layers from the structure of neural network by using a simple template tensor language. And after extracting the description of the network, I calculate the basic pipeline configuration for a neural network on a heterogeneous device. And after this offline procedure, I launched the convolutional neural network on the device along with the inputs frames. So in the online module, we basically first try some pipeline configurations and pick the one which proves to be the most throughput maximizing pipeline configuration for a given platform. So in the next slide, I'm going to show you the whole procedure of training and then running a pipeline stage. Um, let's move to the second slide. Okay. Yeah. So here you can see that there is a phase of training on the system. So basically the system is again NVIDIA Jetson TX2, which was mentioned by Osman. It has 2 Denver cores and 4 ARM A57 cores. So in the training phase, basically my algorithm tries some pipeline configurations, some pipeline stages of 2 or pipeline configuration that contains 3 stages, 4 or maximum up to 6 pipeline stages. And after the training phase, when the algorithm converges, you can see a vertical red line on the in the figure. That vertical red line shows the end of the training phase, and by the end we get a configuration of pipeline which proves to be or is expected to be the near optimal pipeline configuration for VGG on TX2. And then after training, a normal pipeline stage phase starts, and the remaining input frames execute in a pipeline fashion. So we can see in this figure that after the training phase ends, we have achieved a pipeline stage which has very negligible length of bubble or bottlenecks, and the throughput is maximized as much as possible. The best configuration in this training was found to be a 3 pipeline stage, and with the distribution of layers such as, so since VGG 16 has actually 21 layers, and 16 out of 21 are compute intensive layers. So the breakdown is such that the first 6 stages are packed into pipeline stage 1. Next 5 stages are pegged into pipeline stage 2, and then other 10 stages are pegged into pipeline stage 3. With this, since at this point I had an idea that okay, algorithm is doing something better and it is converging to a result which seems to be better, but in order to compare it with some baseline and to make a sort of analysis that how much efficient this scheduling algorithm is. Basically, it's not a scheduling algorithm, it's a search space optimization which I am doing on the top of this scheduler. So in the next slide, I'm going to show some comparison uh, mm, between the brute force algorithm and the pipe search algorithm, which I have used for the training. So since we know that brute force algorithm is a case where every possible search point is tried and tested. So to make this analysis in a real time, I made a small search space of 4 cores instead of 6. So I again used NVIDIA, but this time only 2 Denver cores and 2 A57 cores. and the application is VGG16 again, and I used 2000 input frames to test the comparison. So within this table, actually, that the exhaustive search or the brute force algorithm took 1970 different trials to test which pipeline stage could be the better one, and it took almost 8100 seconds. As compared to the pipe search algorithm, which converged within 41 trials, and the overall training time of the algorithm was 116 seconds, and the execution of 2000 frames ended in 2900, approximately 3000 seconds. The good thing which I observed in this experiment is that after trying all the configurations, the best configuration turned out from exhaustive search or the brute force search was the same as the one which is explored by the pipe search algorithm. So what it is, the configuration is basically this sequence tells that it is better to have a pipeline stage of pipeline of 3 stages, and the first stage should get 7 layers, first 7 layers, followed by 4 layers in the second stage, and the last 10 layers in the third stage. Since now I have 4 cores, but the pipeline, we have 3 pipeline stages, so first pipeline stage gets 2 cores and the other have only 1 A57s. So the point here is that since the cores are heterogeneous, and we initially, when we start the search, we don't know that which core is faster or slow. The algorithm doesn't know. That's why we run some configuration so that we can find a better one. And the seed which I compute from the offline or the pre-processing module is quite similar to what is explored. So if you see, there is a difference only in the distribution of 7, 4, 10, but the initially which I suggested in the offline module is 6, 5, 10. So this actually gives a conclusion that utilizing the seeds based on a network descriptors can help us to reduce the research space, and we can actually make a comparison online. So with that, I end my talk, and thank you very much. So
thank you, Pira. Thank you very much to give us such a deep insight. And as the time is moving on, I'm now taking back the moderator role, so you cannot show anymore your presentation. And I will now introduce Niels Kuxa. I hope I say the name right. Hi, Niels.
Hi.
Hi, good, you're there. And I will introduce you. Niels Kuxa studied computer science. I will now turn you also on. Studied computer science at Bielefeld University with a focus on the field of physics. He received his bachelor in 2013 and his master's degree in 2016 at Bielefeld University with a semester abroad at the Queensland University of Technology. He is now working in the research group Cognitronics and Sensor Systems, Center of Excellence Cognitive Interaction Technology at Bielefeld University as a research associate since 2017. And he will introduce now to us the topic of smart home and AI by presenting an interconnected research apartment, integrating smart technologies in different ways, for example, smart mirror, smart kitchen, or smart door. So now I'll let Niels talk. I will also now, I see that we don't see you yet. Let me just try to get you back. So I put you back. The camera, maybe it works. Yes.
Yeah.
So it's up to you now, the show.
Hi. Yes, as already mentioned, I'm Niels, and I will now talk a little bit about our smart home use case we had in LEGaTO. So it's more about AI at the edge. And as already mentioned, before LEGaTO, we were also already involved to some smart home environments, somewhere within our facility, like the one on the left, where we have different kinds of sensors integrated into one of our offices. and measuring stuff and so on. Some are without our facility in cooperation with different companies. For example, LEGaTO, which is a huge hospital and care facility company here in Germany. I don't know if anybody knows it or not. Doesn't really matter. And another one is with Miele, and they all have somehow some similar fields or areas which they are focusing on, and some are more specialized on one part of a smart home. Like the Miele one is more focused on the kitchen and so on. So usually what we always do in our smart home environments are some typical use cases we always tackle, which I just briefly mention here, like an intelligent door, which recognizes the user and opens automatically. And it's also recognizing obstacles if the door should not open, like a bag which is in front of the door, or a finger within the door, then it should not close. Some kind of a dialogue assistance, like virtual AI, which helps you with different kinds of the everyday life, like organizing your calendar, stuff like this. The kitchen I already mentioned with Miele, where you have basically an assistant which helps you or guides you through cooking, and tells you where everything is within the facility, and so on. And we have a fitness chair where you can just do basic training things. And last but not least, the magic mirror or the smart mirror to interact with the whole flat. And what you already can see is that we have some similarities between all of those things. They are always using some sort of control interface, like gesture or speech, and you always want to know who's in front of it. So we always most often have a face recognition also built in. And what we always focusing on is energy efficiency. Sorry, not energy efficiency, but data security. So in the past, we always used beefy hardware to tackle all problems. Like the kitchen has one 1080 integrated into it to do all the neural networks, or the smart mirror has two graphics cards inside of it. So every room in this apartment is taking up about 600 watt. So which is a huge, but it was amount, but it was never a focus. So we always didn't focus on it. So for LEGaTO, we took one of those demonstrators which has integrated the most features, which is the smart mirror, because you have a gesture recognition, a face recognition, object detection, and so on, and speech recognition. So it was a good use case for LEGaTO. And what is a smart mirror? I don't know if everybody knows it. Here's an example for one of our demonstrators. So basically, it is a semi-transparent mirror with a display behind it. So you see yourself like a normal mirror, but through the display we can show different kinds of information to the user. And because we know which user is in front of it, those can be personalized. Like every time I'm in front of the mirror, it shows me the cafeteria offering, or the public transportation schedule, how I can get home. And we always want to be able to control it, so we have gesture and voice recognition for it. So one of the main goals within LEGaTO was the increasing the energy efficiency of our use case or the demonstrator. In this regards, we tackle like 10x more energy efficiency, and we have the smart mirror as a demonstrator for this. And as a goal, we set like 10 FPS would be nice, because you don't need more for a smart mirror, but it should be around 50 watt, so a lot less than before. So first of all, to have a baseline and a starting point, we built 2 different prototypes, which has the biggest and best hardware you can think of, just to see where we are starting from. So on the left, you can see the general modules which are running within these this smart mirror, which is basically object and gesture recognition and face recognition and speech recognition and so on. And those are all running in parallel. And as the base application, we use the Magic Mirror project, which is open source. So yeah, we don't have to build up all modules by ourselves, but we can also integrate different kinds of information application which are publicly available, which is also nice. So in regards of how many neural networks we built into this demonstrator, here's are some names for it. These are not all we are using, but you can already see those are a lot. So for face recognition, we have 2 different kinds of neural networks and SVM classificator. So for object and gesture, we are using YOLO with the darknet framework. And we are also getting our own data set of fan gestures for this and training ourselves. Yeah, and deep speech for speech recognition and so on and so on. And we're also now trying to collect user behavior data of the different users which are using the smart mirror, which is currently not so easy because of our situation. The mirrors here in our office, in our building, and yeah, as you might know, Corona. So we don't have that much data yet, but we are planning to gather more and trying to train DNN for behavior prediction on this. What you can also just see here is we are heavily using YOLO. So as one starting point for this project, we looked at YOLO at an early stage on different GPUs, how fast and how efficient is it running, and what kind of hardware are we aiming at. So we started with a 1080 Ti, as mentioned. On the camera, we have a maximum of 30 FPS because we are using Intel RealSense, which just gives us 30 FPS. If you're running on a video, you can get much higher FPS numbers, so that's why there are 2 of them. But you can see as soon as we introduced specialized cores within the 2070, we get a huge benefit of energy efficiency. So we thought, what kind of hardware can we also use to use those cores, which turns out to be the NVIDIA Xavier modules, which are below our 50 watt line, which we wanted to spend a maximum for wattage, and they're faster than the 10 FPS we wanted to have. And you can put it into different modes, so that's also nice. Then we can combine maybe multiple of those to get our mirror running at our desired power level and performance. So then there was the idea born to basically distribute every part of our smart mirror onto different modules, which are specialized in some sort of computation, like the NVIDIA for some neural networks, or I don't know, an FPGA for image calculating and scaling and so on. Yeah, and some different ARM core stuff for the general computation. So before we couldn't interconnect those to get the benefit out of multiple microservers. So our group is also developing hardware where we can combine those microservers, which is seen here for the Edge server, which is currently under development. And the idea is that we have different kind of communication infrastructure that those modules can communicate. And we are developing this within the COM-HPC standard, that we can use modules from different vendors and place them onto our server, and they can communicate and interact with each other. Yeah. So the idea is to bring the mirror onto an edge server with multiple microservers. Because this is ongoing work, we built ourselves a test bed before, and we started with one NVIDIA Xavier module and wanted to see how far we can get. And one is not enough to run the whole mirror, which was to be expected. We got about 6 or 5 FPS in each detection running at the same time, and it consumed about 42 watt, so it was a bit too much for it. Then there was the idea born to couple 2 of those modules and using the LEGaTO tools to offload part of the computation onto a second module, which you can see here. So basically we have 2 NVIDIA Xavier modules interconnected via PCI, and they're building a virtual Ethernet. And now we have 2 which can work together. So we optimized the gesture and the object detection with the help of BSC with OMS at cluster to run on the second Xavier. So basically you write OMS pragmas, and OMS handles the communication and everything between those 2 modules. And you can see on the right basic structure how it's working. And each of those steps are running parallel, so that the communication and everything is hidden within the execution time of YOLO, which is quite big. And we managed to get the same performance on the second run than running on the first module. So we have no loss in performance. But of course, we have a little bit more CPU usage. But the GPU of the first module is freed up so that everything can run. So we managed thereby to get a FPS in each of the in all of those recognitions running simultaneously of 16 FPS. And the 2 Xavier combined are using 55 watts because of the power mode we can set. And that was basically the maximum we could achieve so far, but we are aiming to get this even higher. So just for recap, our performance goal was 10 FPS, which we achieved. But we overshoot the budget of the wattage a little bit, but this can be, I guess, get even better than this at a later stage. Yes, I'm almost finished.
Yes.
So we did first optimizations and get the performance up. The introduction of tensor cores and the second optimizations get us even higher. But we also see that the wattage consumption was greatly reduced. And if we combine those 2 graphs into how much wattage we spend for each FPS, we see that we already are better than what we wanted. Just slightly, but we are. Yeah, this is just a summary. So heterogeneous hardware is a good approach for it. We want to combine them with the flexible, high-speed, low-latency communication via PCI Express, which will be on our hardware, on our edge server. And we're using OMSAT cluster for distribution, and we get a significantly energy improvement up to 12x on our demonstrator. That was basically all.
Thank you, Niels. So thank you for this deep smart home inside. I hope I have soon a smart home. And now we're going to Hans. Hi, Hans. Nice to see you. Good, and we hear you. Perfect. So I shortly introduce you, and meanwhile, I also give you already the moderator role. So we are a little bit moving on. Hans is CEO and co-founder of MBDL. I hope I say it right. He received his master degree in complex adaptive systems in 2012 from Chalmers University of Technology and holds double bachelor degrees, engineering physics and industrial and financial management. And Hans has, through his career in industry and academy, worked with R&D in the field of machine learning and deep learning on a range of challenging problems. Hans will introduce the energy problem in deep learning, both in learning and interference. So I let you talk because you can do it better than me. Great that you're here. And we see your presentation. It's perfect.
Excellent. Thank you very much for that introduction. So my name is Hans. I'm the CEO and co-founder of Embeddle. Embeddle is a spin-out from the LEGaTO project, and that is what I'm here to talk to you about today. So there's three enablers for the current AI boom that we see today. We have much more data and also annotated data that we can learn these systems from, and much more compute power, and there's a lot of improvements in machine learning algorithms. There is hundreds of sorry, that was can you see the whole of my presentation, because I have some GoToWebinar that I cannot remove in front of it. Yes, I just continue. Okay, and we have applications in all industries. So that is all sunshine. So what's the problem then? As you can see in this graph from OpenAI, is that these models, you have the time axis on X, and you have the operations that require to train these models, the dots in the graph, and on the Y-axis you actually have exponential or a log scale. So this computation that is required to train these models actually grows exponentially. And this is a problem. It's especially a problem when you go to embedded systems. Here you see a GoogleNet. That was a dot on the last graph. That contains 11 million parameters, and it carries out over 2 billion floating point operations to predict one frame. This is a lot of computations, and it leads to systems that have difficulties in meeting real-time requirements. And all these operations uses energy. So especially for battery-powered devices, this is a critical issue. And also for consumables, this is a great issue because this hardware is quite expensive. So it limits the innovations that a company can do using advanced AI. So surely the research community must have done something about this and found solutions. And yes, partly so. And there's a lot of research in how to make deep learning more efficient. But this meta study from 2020 is what we found out in the beginning of the LEGaTO project as well, that there's really no one comparing with other methods. So you see here on the Y-axis is the frequency of number of papers that compare to this many others. So there is 21 papers that don't compare to any other method, and there's 22 that compared with just one. So out of these 81 papers, there's actually more than half that compare with 0 or 1 method. And this is pruning is just one method of many different approaches of optimizing deep learning. So we realized that this is an issue, and we wanted to do something about this. So as you can see in the beginning, machine learning is a fast-growing field. It's a lot of research, but this field of optimizing these models is orthogonal to the actual model development itself, and there's a need for systematic evaluation of these models. And also there's a need for combining and unify these methods. So we thought, well, this is a good opportunity to make a spin-out out of this. So we created Embeddle, which stands for Embedded Deep Learning. that has as a mission to do efficient deep learning in automotive and IoT. So we're a spin-off from Chalmers University and the LEGaTO project based in Gothenburg. We are now backed by private funding and also research projects from EU and Tetramax. And we're part of various networks, both international, European, and national in Sweden. The challenges that we have set out to meet are to meet real-time requirements, reduce the expensive hardware, reduce the cost of hardware, reduce the development process as well to reduce the time and shorten the time to market, and work as a partner for optimizing models then for companies. So we're interacting with the tools that people use today when they develop deep learning models, more specifically TensorFlow and PyTorch. And the customer gave us requirements in terms of execution time, throughput, memory limit, etc. And we would then optimize these models to meet these requirements in an automated way. And then we have interfaces to various hardware backends, CPU, GPU, FPGA, and ASICs. And this is very much thanks to the LEGaTO project that we can add then support for these hardware backends, because our background is in the machine learning and algorithms and not on the hardware side. So what kind of performance can we actually get with using our tool chain? So here's some benchmarks on 3 different models, ResNet 18, VGG 16, and YOLO version 3 on different hardware. The first one is Intel Core, which is more of a desktop CPU, but the other ones are intended for embedded systems. And we can see that the optimization depends on the model, and it also depends on the hardware. So it's very difficult for us to say how much can you optimize, because it's very dependent on the model and the hardware and the problem itself. But we can see in this graph that we typically can reach something between 2 and 11 times more energy efficient, which is quite good. And the same is with execution time as well. Same here, that we can do quite some improvement in execution time by optimizing the model. See if I can show a little bit of a demo here. So this is me and Henrik walking around the office. The one above is optimized and the below is not optimized. Now you will see me doing some jumping in the office. And you can see that for safety critical applications, for example, it can be quite interesting to have high frame rate, obviously because of the safety that it follows the object quite much better. So this is on the same hardware. So to summarize, Embeddle is spun out from the LEGaTO and Chalmers University, and our mission is to make deep learning efficient in automotive and IoT. And our optimization approach bridges the deep learning software tools and hardware platforms. And by using in Embeddle, you can reduce energy consumption, hardware cost, free up time of internal resources to focus on the core problem, and you can reach faster time to market for products. That's the purpose of what we are doing. And we're always looking for partners, both industry and academic partners for collaboration. So please reach out if you find this to be interesting. Thank you very much.
Thank you very much, Hans. Thank you also all the other speakers. Thank you very much. This was basically so much that our participants are they don't come after with the questions. So anybody who has still a question, please write it down, but I'm the first. So directly to Hans, as you're still in the picture. You are basically an SME spin-off who is now doing AI. Do you already have customers? I don't hear you.
Sorry, now it's this mute thing. Yes, so we have customer. Yes, and it's official, so we can say it's the subsidiary of Volvo Cars, Zenuity, or now they rebranded to Sensact. So they are a customer of us, and we've done verified the technology with pilots, and now they are on a license, a proper license.
Thank you. Yes, say again more. I didn't want to stop you.
And we are now looking for more customers. So we're talking with customers both in Europe and also in the States.
Great. So now comes, I will give you, Noshra and Narang, I will give you now you can ask a question. So let's try. I give you the,
yeah, thank you. Thank you. Yeah, thank you. So I think I really appreciate all the individual initiatives on optimizing the energy efficiency. But my question is a little larger canvas and a higher level. And I think this has been actually pinching me for the last couple of years since AI became really popular. So we talk about sustainability, we talk about energy efficiency along with AI. Are we not creating paradox? So because AI itself, by its default nature and by its DNA, it is compute intensive, energy intensive, resource intensive. So I think I do not see any initiative. I've also been attending AI and sustainability tracks and webinars. We do not find any discussion happening. How do we optimize the AI itself? Do we really need to go whole hog for using too much of intelligence? Everywhere, each use case, everywhere, go deep learning, go this thing. Is there any initiative, any discussion happening on any platform, where we can talk at the macro level that do we really need this much of artificial intelligence? Every individual use case that we start picking, everybody is today gung ho about AI. This is my question. It's a larger problem, I know, but not commenting on the importance of the current work. And I think these are very, very critical initiative. Today I was really excited with the kind of work because I'm a hands-on design engineer. But the question is really larger. AI. Yeah.
As time is passing, we need a clear question. So can you just?
Question is there any initiative to address the optimization of AI or sensible, appropriate AI for different use cases rather than going whole hog using maximum intelligence and consuming a lot of resources and making it less sustainable and less energy efficient?
Okay, let's try. Is somebody of the speaker, Hans, Niels, anybody feels like answering this?
No problem. No problem.
No.
It's okay. I understand.
The question is too difficult. So we are passing on. I'm giving now to Ahmed. I'm going to ask the question. One moment. One moment. I have to here. Ahmed Seboshi. Hello. Do you have any information regarding IoT cloud energy efficient service composition selection? One moment. My speakers. Are you still there, my speakers? One moment. I give you all the mic. Anybody? Niels, Osman, Pira, Hans, do you have an?
Sorry. Yes, sorry, I could answer the first question. I somehow got muted. So sustainability, I think this is important. Sustainability of let's say AI. I have not seen, at least on the European project space, I don't see specifically a project devoted to that important topic. And it's sort of like Jevon's paradox, right? We get a lot of energy savings, and then we say, since we have lots of energy savings, let's throw some more, let's say, computing power at it. Let's add some more layers, etc. And then in the end, we end up spending the same amount of energy. So I think
yes, that is my point. Exactly. Yeah. Thank you.
So we have to tackle that. I think if there's anyone from the European Commission listening to this talk, I think it would be really sorely needed, in personal opinion.
Yeah, we need to start discussion on this topic also. How do we talk about appropriate or reasonable amount of artificial intelligence in any use case rather than going full hog based on our requirement? Thank you.
Okay. Okay, thank you, Osman, thank you, Mr. Kishore. And now, once more, back to the question we just had. Hello, do you have any information regarding IoT cloud energy efficient service composition selection? It's from Ahmed Sibushi.
So what is meant with composition selection? Is that choosing to do the composition on edge and cloud, or a combination of those, or?
I will now let him talk, as we are over time. So anybody who feels like staying in the cafe, welcome, because we have so many speakers, so it goes longer. But I now will let Ahmed speak. One moment. Ahmed, one moment, you're coming. I think he left. He's not there anymore. So we cannot answer. So I'm going to the next question. Anne Flint, could you give a quick comment on what the difference of this platform is to Google's Colab?
Was that to me?
Yes.
Okay. So Colab, I have not used Colab myself, but it's something similar to Jupyter Notebook, right? You have a notebook and you do various code blocks and you execute them. Or is it more like Amazon's tools that they have for deploying deep learning into IoT?
The problem here is that we cannot, let's try that. Anna wants to talk. The counter questions don't work well here. So basically we can try to get her.
Okay. Okay, I can try to answer it, but I might answer it very wrong right now. So if it's more of a Jupyter Notebook, so I mean, you can develop your deep learning model in a Colab or Jupyter Notebook or Python or whatever you want, using your favorite tools like PyTorch, TensorFlow, and embedded is a Python library in itself that you would import as any other Python library and optimize the model and generate an optimized model for a particular target. So this can obviously be put behind a cloud service, and then we would have something similar to what Amazon is doing. And that's something that we are considering for the future. But right now we're using it as more of a standalone Python tool where we work closely with the company as well to learn more about the specific problems that they have, because it's not only this problem, there's sort of tangent or closely related problem that might need some special implementations.
Okay, thank you. So we are going now. Thank you. Anna says already, thank you. Thank you. So we're going to the last question because we're really over time. So Peter Malik. There are many methods to improve efficiency: parameters, reduction, compression, quantization, but a lot of it depends on good low-level support. Can you give quick summary what really work at the moment, what really improve efficiency on what hardware? I think this is not a small question. But give it a quick shot.
And it's not a small question. It's also a bit of a sensitive one, because that's sort of what we are packaging and sell as a black box solution. But you're absolutely right. There's a lot of things that we do internally that we're really excited about, but it does not exist any hardware support for it. So we cannot really deploy it, so we would not see the benefits. For example, when you do sparse optimization so that you will have sparse neurons, sparse segmentation, especially then the weights, the sparsification of weights, then you need to have a runtime that or hardware that can take benefit from that. And you can customize that in FPGA, or you can do your own ASIC, but most people will not do that, but use, for example, NVIDIA GPUs. And then you need to do, for example, structured reduction of parameters where you actually are sympathetic to the hardware. And that's sort of what we do, given what model you have, what optimization methods should you do according to this hardware target that you have. And so it becomes a combinatorial problem of doing this, and that's basically what we do in the company.
Thank you. So I think we're really over time. So it's thank you for everybody being here. Thank you. And it's always challenging when we have a lot of speakers, and there are many more questions out there. So if you want to ask more questions, dear participants, send it to me, Carmen@grassrootsarts. You will get tomorrow latest another email from me. And then I forward it. Please say to whom you have a question, and I will forward it either to Osman or to Pira or to Hans or to Niels. And so once more, thank you for you all being here. It was a pleasure to host you, and I got already a lot of great congratulations for this cafe, because it's an interesting theme. People love it, and so I will send you afterwards the recording, and you may allow me to publish it in the AI for You channels on YouTube. Please send me back an okay or red light. No, it's okay. And thank you very much, and hope to see you one day in the real world. Bye-bye. Bye-bye. And next week is a new cafe on Tuesday, but you get invitations. Bye-bye. Bye-bye.
Bye.
Bye-bye.